Well, hello, ladies and gentlemen, boys, girls, fellow Homo sapiens. Welcome to the wonderful world of today. Here's an example of using this work energy theorem, solving a problem using kinetic energy, and taking a look at maybe going back and using some formulas we have already had. So here's the problem. You've got a 50 kilogram diver, steps off a diving board and drops straight down into the water. The water produces an upward average net force of 1,500 newtons. Call that drag or friction if you wish. If the diver continues and comes to rest 5 meters below the water surface, what is the total distance between the diving board and the diver's stopping point underwater? All right, well, let's think about that. So we've got a diver stepping off a diving board. We want to find out basically how tall the diving board is. That's what we're looking at. We can figure this out if we know what the net force is slowing the person down. So this could be, say, an example of a type of problem where you've got a pole vaulter falling into a mat. If we know how fast they were going when they hit the mat, we can figure out if they come to rest, how far in they went, and we can figure out how hard they fell from. So in this case, if I can figure out how fast the diver was going when they hit the water, I should be able to take it backwards and figure out, because we know the acceleration due to gravity, I should be able to take it backwards with an equation we know and figure out how high the diving board was. Then if I figure out how high the diving board was, I should be able to turn around and say, hey, this was how high the diving board was. I went 5 more meters into the water. Where am I going to end up? And that's how we'll approach this problem. Again, start with what you know, mass of the diver. "50 kilograms, yay. Gravity equals 9.81 meters per second squared. Yay! We know this drag force, this force of resistance, is 1,500 newtons average. And we know the distance it fell in the water was 5.0 meters. We want to find the height of the diving board and then add this 5 meters to it in the end. So what do we have? We have diver hits the water. Diver falls down 5 meters. So we have this D that is 5 meters. And we have a force of 1,500. What are we going to do with that? Well, we know the net work. Work is force times distance. Okay, the direction in this case is I'm moving this way, the force of resistance is up, the cosine of the angle is 180 degrees, which means I'm doing negative work in this case. So the work will come out negative, and we also know that must be equal to that change in kinetic energy. So this is what I have at the moment. So we got the diver falling. Well, we know net work is force times distance times the cosine of the angle between them. In this case, our theta is 180. Cosine of 180 is going to be a -1. But we also know this is equal to the change in kinetic energy. Well, when the diver hits the water, they have some initial velocity. But their final velocity in this case, because they stop, is going to be 0. So we have this. So we have the force times the distance times the cosine of the angle between must be equal to 1/2 m v sub f squared minus v sub I squared. V sub f in this case is going to be 0. This is cosine of 180. That's going to become -1. We still have the mass of the diver. We still have the initial velocity. And the initial velocity in this case is what we want to find. We want to find how fast the diver was going when they hit the water. If I know that, I should be able to figure out how high they started, since the only acceleration I have is that of gravity, and I know when I came off the diving board, I started at a 0. So solving here, I get 2FD over m, and there's a negative sign here, must equal the negative v sub I squared. Negative 1, negative 1. We're going to cancel that out. Yay. I want to find v sub I. I'm going to take this as a square root. We know this gives a positive and or negative answer. We're taking the square root. Doesn't matter for us at the moment. We know that if we're going down, call that a negative velocity, right? That's okay. In this case, we could call it a positive velocity if we want. Doesn't really matter. So we have this. This then equals the square root of 2 times 1500 times 5, all divided by 50. Well, 2 times 5 is 10. 10 and 50 leaves a 5 down here. This ends up being, sorry, don't introduce the square root yet. Don't introduce the square root yet. Bad me. This should end up equaling 300. V sub I is simply equal to the root of 300, and that's in meters per second. I have the initial velocity at which it hits the water. The final velocity in the water is 0 for our problem. But here's the deal. Our new final velocity for the other part of the problem of going from the diving board down to the water, we're going to have that v sub f equals the root of 300 meters per second. I'm going to put that over there. We found this. Now, the second part of this problem involves then, you're up on a diving board, we don't know how far, you walk off, come down, you hit the water, there is some height involved, and all we know is we know g, we know the mass of the diver, and we know how fast it was going when it hit the water. Well, we have an interesting formula that says v sub f squared equals v sub I squared plus 2a, in this case delta y. Oddly enough, I can put this in. What do we know about this? We know this is 0. What do we want to find? We want to find delta y. Well, we have the fact that v sub f squared over 2a must equal delta y. Again, let's say the downward velocity in this case is positive. That means our acceleration due to gravity is positive if we pick it down. So if we do that, we have the fact that 300, or root 300 squared, divided by 2 times 9.81, all must equal this delta y. We have the fact then that if we get this and we solve, we have that delta y then must simply equal 15.29 something, and that's in meters. So we have meters per second quantity squared over meters per second squared, acceleration. Our units cancel, and leaving me meters squared over meters, which leaves me a unit of meters, which is good. That's what we wanted. Checking our dimensional analysis, seeing we have an answer that makes sense. Well, we have then that this is y sub f minus y sub I. Well, let's just call y sub I up here 0. This is positive 15. We get the fact that then this turns into being 15 meters. Going back and looking, we're going to have the fact that this is good to 2 significant figures. And I'm going a little quicker than I usually do. I'm just trying to make our videos shorter. This should be 15 meters. It's good to 2 sig figs if we go back and look through all of this. 2 sig figs here. when we do our division, 2 sig figs, we end up getting 2 sig figs in the end. It fell 15 meters here. Then we have down here another 5. So the total distance was 15.29, whatever, plus 5.0, rounded to the ones place. That gives us a total of 20 meters with 2 significant digits. Again, we can't forget our old equations. We're supposed to know them. We introduced the new equation that said net work is equal to the change in kinetic energy. Hope this made a little bit of sense. And I hope you guys are having fun and staying safe. Drive fast, take chances, do inappropriate things with people your own age. Be safe, guys. Miss you.